This is the normal curve scenario. So the first thing you want to do is to put your name in the first spot, and then we're going to study the normal curve. The purpose of this activity is to give you concrete experience necessary for you to thoroughly understand and apply the concepts of normal distribution, the normal curve, and the empirical rule, and apply the concepts in solving practical problems. We're going to have different types of distribution. We're going to categorize data, make distributions, list the elements of both a normal curve and the empirical rule, and then apply the empirical rule to practical problems. If you notice here, we're going to use the example of a wooden floor. Suppose you have a room in which you want to install a wood floor. Below are 3 different floors. They are made of boards of 3 different lengths. The uniform boards give a regular pattern. The normal and random floors appear very similar. We're going to compare the similarities and differences among the 3. So you see the normal floor first, normal data, the random length boards, and finally the uniform length boards. Those are the different floors. Wood floors are made of individual boards, usually of uniform width and varying length. In the uniform data wood floor above is the exception. The boards there are all the same length. When they were cut, the saw was set so that they would all be the same. They form a pattern that is very orderly. As a result, what wasn't used to make the wood floor was a bunch of boards of different lengths. The other 2 floors maximize the raw materials by using as much of the board as possible. In some cases, the only waste in wood is where the knots are cut out. In other cases, even the knotty wood is used. While both of the floors with boards of varying width appear possible, that's not true. Here are the sticks from which the boards are made. On the left is the normal raw materials. The way the wood is stacked, it's difficult to tell if the boards are random or normal. Stacking the lumber may be one way to see the differences and similarities among the boards. And one thing you'll notice is they fit in a much smaller package, but also you can begin to see that some boards, or you could at least see which boards are the longest in this case. What is a dispersion? It is an arrangement of data in which the number or frequency of each item is related to the property, in this case their length. So we see the stacked normal boards here, and you can see they vary up to 60 centimeters long. You can't see the shortest one, but it looks like this one over here is pretty short, doesn't it? Here we've got the random length boards, and you can begin to see some of the differences between the 2. These appear to be much more varied, don't they? And you can see the shortest one is around 10 centimeters. The uniform length boards are all 35 centimeters long, except the ones at the beginning, at the end. So I'll show you that on the floor. You notice here at the beginning, every other board is half as long, and at the end, every other board is half as long. But otherwise, all the boards are the exact same length. Random or normal. When you consider the stacked lumber above, you can easily see that the uniform boards are significantly different from the rest. So that's all we're going to talk about, the uniform length boards. We're going to consider just the random and normal variety of boards and how they differ. You can begin to see the differences by just looking at the stacks of each. The random stack is much more varied, as I said. Their normal stack, by contrast, isn't. We're going to emphasize the differences by putting the boards into 5 stacks, such as what I've got in the pails next to of each size of boards. The next graph below shows the normal boards. Most of the boards seem to be near 35 centimeters long. There are fewer of the shortest and longest boards compared to the random boards. So if you notice here, this is the stack of those between 10 and 20, 20 and 30, 30 and 40, 40 and 50, 50 and 60. If you notice, most of the boards are between 30 and 40 centimeters long, and then fewer of each of the ones on each side of that, and then fewest of all of the shortest and longest boards. Whereas in the random stacks, each stack, the 10s, the 20s, the 30s, the 40s, and the 50s, all appear to have about the same number of boards. Here are the lengths of all of the boards. I put them all in here because we're going to calculate some of their statistics. We are going to analyze their statistics. We're going to find their minimum, first quartile, second quartile, third quartile, maximum, average, and standard deviation of the population. Then we're going to make graphs of each one of them. Let's start with, how do we calculate the minimum? Well, we could type equals minimum, and when we do, it would give us the minimum of each one of them. But what we want to do is use the quartile dot inclusive for each one of the boards. And the reason for that is, I'm going to show you in just a second, when we highlight all of the boards and we see that the the 0th quartile is the minimum value, so we're going to use the minimum here, and when we do, it gives us the length of the shortest board. When we pull that value down, if you notice, what happens is C14 and 276 used to be 213 and 275. So what we want to do is make sure when we pull them down, they don't change. And we do that by pressing F4 for each one of the different addresses in the array. Then when you do that, you see a $C, $213. That just means that that value isn't going to change. $K, $275, that means each of those values isn't going to change. So when we pull those down, all of them are the same, and if you notice, I pulled it all the way down to maximum. But we don't want each of them to be the minimum. We want to change it so that in the second box we have the first quartile. In the third box we have the second quartile. In the next box we have the third quartile. And in the last box we have the fourth quartile, or the maximum value. And when we do, we notice that for the normal boards, they vary anywhere from 10 centimeters to 60 centimeters long. We have the normal data, and if you notice here, here's the box and whisker, goes from 10 to 60, and the length is anywhere, the Q1 is here at 20, about 8, and Q3 is about 42. Gives them here 35, or 28 and 42. Okay, so let's do the same thing for random boards. Equals quartile dot inclusive, and our array is going to be all of the normal boards, and we want to start with the 0th quartile. And once again, we're going to F4 each of those so that when we pull them down, the values don't change, and all we have to do is change the quartile to first, second, third, and fourth. You notice the random distribution here above and the normal distribution, and you can see how their box and whiskers agree and disagree. In both cases, the shortest is 10 and the longest is 60, but the random boards are more spread out. The normal boards are more concentrated around the middle lengths, and you can see that looking at their data here. We want to find the average, so we would say equals average, and we want the average of all of these boards here, and we want the average of all of these boards here. And we just highlight the ones that we want to average. And if you notice, the average comes out pretty close. 35 is the average, and 34.11. Finally, we want to find the standard deviation of the population, equals STDEV.P for population. And here is our population over on this side, and our standard deviation of the population over here. And one of the things that you will notice is that the standard deviations, while the means were pretty close, the standard deviations is much bigger for the blue data, And that's illustrated by showing that the box for the random data is bigger than the box for the normal data. Okay. The other thing that we want to do is we want to make a histogram like you see here. We want to find the frequency, and to find the frequency we're going to highlight all of the boxes that are next to numbers, not the total box, because we're going to do something different with that. And when we do, we type equals frequency, and we're going to get the data, which are all of these boxes, comma, and we're going to get the bins, which are right here in the middle, close parentheses, and now hold down the Control and the Shift key before you press Enter. That's the only way you're going to get all of the boxes to fill in. Do the same thing for the normal data. Highlight the ones that have the 9.9 to 60 equals frequency, and the data, and the bins are right here in the middle again, 9.9 to 60, close parentheses, Control, Shift, and then press Enter, and you get those. Sum of these numbers, and we get 567. I'm just going to copy that cell over to the other side, and if you notice, both of them have 567 floorboards in them. All right, now let's make a graph of each one of them, and to do that, you highlight. Let's make a frequency chart. Here's how you do it. Highlight the data that you want to find the frequency of, or that you want to have as the columns. Insert a column chart. This does not look right yet. We want it to be a different type. So up at the top, go to Design, and let's select the right one. It's not the second one. It's the third one. And the other thing that we need to do is click on the data, because we need to change their fill to be orange rather than blue. The other thing we want to do is to format data series and take away the gap, so the gap is 0. Now it looks a lot like the graph that we see pictured there. We're going to change the chart title to normal. But the other thing that's, all right, we're going to, after we move the chart over, we're going to change, if you notice the categories here, the horizontal axis is labeled by these frequencies. We're going to change it so that those match up. And the way we do that is we click on the data, right click, and go to Select Data, and we're going to edit the categories so that they are now going to be these frequencies right here. Now our graph looks approximately like the one right above there. Do the same thing for the random data. Highlight the data, insert a column graph, change the design to the third one, change the title to random, change the bars, right click on the bars, format data series, and remove the gaps, axes, so that it's the frequencies. And now the graph matches the one above it. And there you have the two different graphs. Now the thing that I'd like you to notice is, in the normal distribution, there are more of the average size boards. In the random distribution, there's just about an equal number of each. We saw the same thing when we made these categories of boards above. The random had just about the same number in each category, and the normal had fewer of the shortest and fewer of the longest. If you notice, those two, this graph matches the stacks of lumber for normal, this graph matches the stacks of lumber for the random. And then you don't get the points until your graph looks like mine. Make sure you type yes in each one of these two boxes if you have the right point title and labels, if you have the correct data heights, and if your graph is clear. All right. Here is that box and whisker plot that we were doing before. But here's a distribution that shows all of the lumber stacked up for the boards, for the normal boards. This is an ungrouped frequency distribution. Up here, we grouped them by tens. Down here, these go from the shortest boards to the longest boards. You have 10 centimeter boards, 11, 12, 13, all the way up to 60 centimeter boards. And it shows how the two graphs look. I did the same thing here with the normal boards. And if you notice, the shortest, the 10s, here's the 35 centimeter boards, and here's the 60 centimeter boards. That's for the normal data. For the random data, you can see that the boards do go from 10 to 60, but there's no pattern in how long each individual board is. What does that mean? Well, when you make a dispersion of the data, when you stack the lumber of a ungrouped frequency distribution, you see here's the shortest boards, 10 centimeters long. Here's the longest boards, 60 centimeters long. And this is the frequency of that. So the shortest boards, there's 1. The 35 centimeter boards, there's about 23. In the random distribution, you can't really tell much of anything. Now, I did add some lines to each one of them. In each one of them, the lines are, the mean is in the middle. 1 standard deviation each way is the other line, and then 2 standard deviations each way I could do on the normal distribution, but I couldn't on the random because if you notice here, our standard deviation, and when we do, we get 14.76. Well, if you take 34 minus 14.76, you get 19. Minus 14.76, you'd get 5. But there's no boards that are 5 centimeters long. The shortest is 10 centimeters long. So you can't get 2 standard deviations less, nor can you get 2 standard deviations more. The empirical rule talks about this bell-shaped curve for the normal distribution. We're done talking about random distributions because there's no pattern that develops. The middle is the mean. Approximately 65% of the boards will be between, or 68% of the boards will be between 1 standard deviation below to 1 standard deviation above. 2 standard deviations below to 2 standard deviations above will be approximately 95% of the data. And then 3 standard deviations below to 3 standard deviations above, 99.7. Virtually every single board will be within 3 standard deviations, which you can't quite get 3 standard deviations with the boards that we have. And the reason for that is if a standard deviation is about 10, 35 minus 10 is 25, minus 10 is 15, minus 10 is 5. So 3 standard deviations, the board would be 5 centimeters long. But the shortest boards are 10 centimeters, so we couldn't get 3 standard deviations below. Here's another view of that stacked lumber, and it shows the other side from the shortest to the longest. Okay, so let's answer these questions. What percent of the boards would be shorter than average? What percent of them is in this section over here? Well, basically what we want to do is we want to take our normal distribution and we want to say what percent is below 50%. Well, here is 50%. It's in the middle. What percent is this right here? What percent is shaded here? Well, it's exactly half of the boards are shaded. So we would say, what percent is that? It is 50%. One standard deviation of the mean. Well, if you notice here, this chart tells us, this chart tells us how to fill in the standard deviations. I'm going to copy our normal curve here, and we're going to fill in the percents. Let's fill them in. How does that work? Well, this 3 standard deviations is 0.5%. This is 2.5%. This is 16%. This is 50%. If you notice, I'm getting them from right over here. This is 84%. This is 97.5%. And then 3 standard deviations above would be 99.5%. So let's see here, what are they asking for? Within 1 standard deviation of the mean. So we mean from here below the mean to here above, or in other words, 84 minus 16 is 68%, which matches our first rule. Approximately 68% are within 1 standard deviation each way. Within 2 standard deviations each way, well, it says it's 95. Let's do the math to make sure that works out right. We would have 97.5 minus 2.5 is 95%. So it does match, and we could say 95%. 3 standard deviations each way, it says, is 99.7. Now your book actually says 99%, and that's partially because we want to make sure you know that it's possible for you to have a board that's shorter than 10 centimeters and longer than 60 centimeters, but it's very unlikely. What percent of the boards will be less than 3 standard deviations? Well, you could say 0%, but if you were using the book, you would say about 0.5%. Either one would be correct. Okay? And then the last one is more than 2 standard deviations below the mean. Or in other words, we want to go from here all the way forward. Well, if from here to here is 2.5%, and there's 100% total, when we subtract that, we would find that we would have 97.5% of them would be more than negative 2 standard deviations. Is between negative 1 and positive 3 standard deviations. In other words, we want to go from here up to here. I'm going to change to black so that you can see what that looks like. We want to do this area right here. Well, this is 16%, and this is 99.5. So if we take 99.5 minus 16, we would get 83.5%. And we could also say 84 because essentially it is all of the rest of them from 16% on up. Lastly, we want to talk about what length of boards are we talking about. What length is the average board? Well, if you notice here, it's right in the middle. The average board is 35 centimeters long, which matches our data up here where we said the average was 35. Next, it says, what's the standard deviation? Well, it says the standard deviation is 9.6, but you could round it to 10 and that would be a good approximation, is round it to 10. So 1 standard deviation less than 35 would be 35 minus 10 is 25 centimeters long. 2 standard deviations longer than 35 is 35 plus 10 is 55. What percent of the boards will be shorter than 15 centimeters? In other words, on this chart here, we want to know what percent is it that's shorter than this. Well, this is 2 standard deviations below the mean, right? And 2 standard deviations below the mean, according to our chart, is at 2.5%. So we would say 2.5% is shorter than 15. What percent are between 25 and 50? Well, here's 25 and 55. We want to know the percent from here to here. Well, we said this is 16%, and this number up here is 97.5. So if we take 97.5 minus 16, we get 81.5%. And lastly, what percent is longer than 35? We want to know how many of the boards are longer than 35 centimeters. Well, if you look at the picture here, you can notice they want to know what percent of the boards are longer than average. Well, it's going to be 50%. When you're done, you will have 35 points on your assignment. If you have any questions, give me a call.